I will try to specifically tell about something which will be very close to my domain as well, and which will be very close to PC Moranovich as well. So, first of all, congratulations to the first year and second year to conducting this National Statistics Day after 3 years. So, I'm very happy that this is happening again.
And after 2023 last hoyechilo.
Yes.
Right.
So, as we all know, in June 29th, India observes the National Statistics Day on the birth anniversary of Professor P.C. Moranovich. The day was instituted by the Government of India in 2007 to recognize his contribution to statistical science and to highlight the role of statistics to national development. Now, Susuma sir already highlighted that P.C. Moranovich was not a statistician, he was basically a physicist. So, he studied physics in Presidency College, where he has served as a distinguished faculty as well in physics. And during his visit in London, he came across a copy of Biometrica. It is a very popular statistical journal, and was struck by the power of statistical reasoning to describe natural phenomena. He returned to India and began applying statistical methods to physical and anthropological measurements. So Moranovich came to statistics through physics. He understood from the ground up that the physics world does not yield clear deterministic form. Measurements have errors, uncertainties that needs to be explained by the use of statistics. He founded the ISI, Indian Statistical Institute, in 1931, where I was also been fortunate to carry out my research work. His most enduring technical contribution, I will just highlight. The statistics people all know, that is the Moranovich distance. So this distance is basically nothing but simple Euclidean distance, but it is been normalized by the covariance matrix. So that means he is basically trying to, the P.C. Moranovich is basically trying to tell that whenever you are in the real world space, the physics is different. Whenever you are in the different data set, the corresponding physics will be different, and the distance would be differently defined. So, since the physics of the data is basically changing, that is why the distance needs to be changed. That is how the Moranovich distance is coming. So, his all thought is basically coming from one fact, that physics, how I will explain by the uncertainty, by the statistics. So, I will also, so my basically the research that I do currently is based on some fluid mechanics problem. And though it sounds a little bit difficult to all of you maybe, but it is very easy in terms of, if I just give one example of river dynamics, like the flow that is happening. So how we will explain the flow that is been happening? Okay, so it is been explained by the use of computational fluid mechanics, and that is also known as CFD. Okay. So what is computational fluid dynamics? It is basically based on one particular equation which is known as Navier-Stokes equation. Okay. Now there is a very interesting story about this Navier-Stokes equation. So this is one of the 7 millennial prize problem. So there are 7 millennial prize problem, that is 7 open problem. If you solve it, you will get $1 million. So one of them has been solved in the last decade by one German mathematician, I forgot the name. The problem was Poincare congestion. So this is one problem of mathematics. And another problem this Navier-Stokes equation gives, that is, you cannot have a smooth solution of this Navier-Stokes equation. So this particular thing you cannot give a proof or cannot give a solution. If you can give a solution, you will get a $1 million. Okay. So how to solve this particular thing? So you cannot solve it deterministically. That means we have to take the help of statistics. That is the uncertainty. So if the deterministic structure is not helping us, so we have to go to the stochastic structure. And that is how the turbulence comes in the flow. Okay. So turbulence is basically the uncertainty and the statistics in the physics that P.C. Moranovich is also trying to suggest. So if the equation is not deterministic, if we have to make it a stochastic equation, so that means we have to give some averaging to the equation, and if we give some averaging, the equation is known as Rayon's average Navier-Stokes or Rayon's equation. And this is the particular problem, Rayon's equation, by which every flow simulation has been done by every kind of CFD analyst. So I think you have seen somewhere, I don't know, in YouTube maybe, or some flow is happening. This kind of simulations you have maybe seen in YouTube. So these kind of simulations, how it is coming? There are some commercial softwares. I hope you have heard about ANSYS. Have you heard about this? Huh? So this ANSYS, how it is generating this particular simulation? So by using this RANS equation, by modeling this RANS equation. Okay. Now currently, why I am focusing on this, because there is some new algorithm that is been coming to the picture and which will be of interest to you, and that is known as physics informed neural network. PINN, yes. So whatever neural network that we do, it is having input output structure, where the input is some data. The data can be numerical, categorical, or pictorial, whatever, and the output, it is trying to predict whatever the input is as close as possible. But in case of physics or PINN, physics informed neural network, the neural network is not only being trained by the data, but also being trained by the physics. Now, how the neural network will be trained by the physics? In the neural network model, there is something called loss function. I hope you all know. The loss function usually reduces the data loss, but in the case of PINN, it will be the combination of weighted combination of data loss and physics loss as well. So that means we have to reduce the physics loss and data loss so that we can get the picture of the flow dynamics correctly. So that is, I was trying to say that so why this PINN is required particularly, let me tell you. In the data that you collect from the, suppose, let me give you one example. Suppose the clinical data that Sir was giving the lecture. So clinical data, you need to do the survey, right? You have to do the drug test, these kind of things. But in the case of, in my field, the fluid dynamics, how to collect the data. So you have a particular machine, you will try to fix that in different locations, then you will try to collect the data. But can you continuously collect the data in each of the positions? Is it possible, feasible? If you collect the data at this point, and the data should be as large as possible, because this is a big data problem. So that means at each point you have to collect at least for 2 minutes or 3 minutes with sampling frequency 100. That means the data would be like 18,000, 24,000. So this will take time. So that means if you collect this data, the next location will be far away from that point. So if there is a distance between these 2 points, that means there is a sparsity in the data. That means we cannot continuously collect the data. So how will we get the information in between these 2 points? So interpolation, that can be happening, ma'am. Kintu problem hocche jeta je ekhane amar 24,000 ache, ekhane 24,000 ache, আর ধরে নিন এখানে একটা ব্লাক বডির একটা এফেক্ট আছে, তাহলে সেখানে আমাকে ফিজিক্সটাও ইনকর্পোরেট করতে হবে। শুধুমাত্র ডেটা ইনফরমেশন দিয়ে প্রেডিক্ট করলে মানে ওটা জাস্ট ওই অটো রিগ্রেশনের মতো হয়ে যাবে। তাহলে we need the information of physics as well. That is how the RANS comes into the picture. So we have to feed the RANS into the neural network model, so that the physics loss will be also reduced and we will get a feasible, মানে এরকম যা হয়ে যায় যে একটা ব্লাব বডি রয়েছে, মানে ব্লাব বডি মানে একটা সাপোজ একটা তোমার গাছের গুড়ি পড়ে রয়েছে নদীর ধারে, তার মানে তার একটা ফ্লো ফিজিক্স তো একটা প্রপার ডিফাইন্ড হবে। সেটা এমন হবে না তো যে হঠাৎ করে লাগলো যে জল উপরে উঠে চারিদিকে চলে গেল, পরে আর জল নেই। তাহলে এই ধরনের ফিজিক্স গুলোকে এক্সপ্লেন করবে কে? RANS. So that needs to be fit. So this particular PINN is have now taken a severe role in the computational fluid dynamics, and everyone is doing research on this now. So that is one of the point, and this is exactly the same instinct that Maulanovis brought from physics into the statistics a century ago. Honor the structure of the system, quantify the uncertainty, do not pretend to more precision than the data and the model jointly support. So he understood that the hardest problem in the physical world are not solved by more precise equations. They are solved by honestly accounting for what we do not know. The measurement error, the model uncertainty, the variability, no deterministic equation will fully ever reproduce. So today in turbulence, in CFD, we face exactly the same problem. We cannot measure every point, we cannot eliminate every source of error. So what we can do is quantify those limits honestly and build models that will acknowledge that. So in the PINN also we are doing exactly the same thing. And Maulanabi's taking the physical structure has been taken seriously and wrapping it in the statistical framework, and that is the honesty about the model. So on this National Statistics Day, I want to pay homage to the man who crossed the boundary between the physics and the statistics and showed us that the boundaries should not have existed in the first place. His distance measure, his sampling methodology, his institution, these are not historical artifacts. These are active tools that we do today. The question he left with us, the same question about every simulation, every trained model, every experimental measurement must answer. How confident about the model, and can we prove this thing? Thank you.